I'll just share my screen. So hopefully you can see that. Yeah. Okay. Well, it's a pleasure to have the opportunity to talk to you about this topic. It's one that I'm kind of quite passionate about. It's the thing that really gets me up in the morning, really, although I still like sort of conventional astronomy. I think, this question of whether we are alone in the universe is a really important one, and it's something I'd like to know the answer to, along with many people, not least people that are just in the general public. I think this is a topic that interests everyone, and a topic where everyone actually has a valid opinion, because we don't know the answer. We don't know if we are alone or whether the universe might be absolutely teeming with life, and potentially even intelligent life. So indeed, I'll be talking about anomalies in astronomical data and how they might be the signatures of advanced technical civilizations. So I just want to sort of give you a rough idea of the topics that I'll cover over the next 45 minutes or so. Well, there's the question, are we alone, which I've just mentioned. I want to talk a little bit about the search for extraterrestrial intelligence and how that arose historically, and when did people first begin to actually understand that it was feasible to conduct these searches, as a little bit of background. I'll sort of bring that up to date in how we think about this area of research a bit more widely than just radio signals or laser signals, for example, but actually just technological signatures of civilizations that are using energy. And when they do that, they modify their environments. And they do that across the electromagnetic spectrum, and maybe even to multi-messenger type signatures. So I'll talk about that a bit more broadly. I'll talk about some recent results that I've been involved in with students here at Manchester. And then generically, I'll talk about some of the projects that are kind of ongoing, looking at astronomical data. We're sort of in this very interesting era where there are many large telescopes. Either they're just become operational or they're under construction. That are certainly going to transform the way that we do astronomy, because they produce sort of very large surveys of the sky. So they're covering large areas of the sky very, very quickly. And so there's just many more objects and the potential for events to happen that are difficult to explain. And we're definitely going to see that over the next 10 years, that there will be things perhaps that we don't understand just because of the huge volume of the universe that we're going to be able to survey. And I think that's really important for me in this research is, how do we widen our perspectives? How do we widen, our sensitivity to actually detecting something interesting? How do we think broadly so that we don't become too narrow and too focused on certain things, but we think as broadly as possible? And connected to that, I'll talk about the future, not just the future of the topic, but the future of our own civilization. So yeah, life beyond. Are we alone in the universe? As I said before, I think everyone has a valid opinion on this. I think my opinion kind of changes from day to day. Sometimes I'm very optimistic, and sometimes I'm quite pessimistic. From a physicist point of view, or an astrophysicist point of view, I think we tend to be pretty optimistic about the answer to this question. We think that, well, if there's life on this planet, the planet Earth, and if there's intelligent life here, and if there's a technical civilization here, then why wouldn't there be, something similar on some other planet, assuming the conditions are right? So as physicists, we tend to be really influenced, I think, at least. I know that I was influenced, especially when I was young, on this sort of principle of mediocrity, that there's nothing very special about us and nothing very special about the planet that we live on, or the star, the sun that we orbit around, or even our own galaxy, or our position in our own galaxy. So sometimes also referred to as the Copernican principle. I think it's quite deep-seated in physicists, that when they discover laws sort of in the laboratory or on the planet, they assume that they just apply universally, and that seems kind of reasonable. So we're attracted to that principle, and also if you look at the numbers, the places where life might find the right conditions similar to our own planet to evolve, then we know that there are many locations, even in our own galaxy, a huge number of stars. We now know that most of them have some kind of planetary system. We know that some of those planets will be sort of terrestrial, they'll be rocky planets, they'll be located such that water can form as a liquid on their surface, that obviously they're made up of the same constituents that our own solar system is made up of, so there's lots of interesting elements and chemistry potentially that can happen and possibly lead to life. And if you think about the universe as a whole, then of course, there's a huge number of galaxies, so an enormous number of planets in total in the universe, something like 10 to the 23 in the visible universe. So all those numbers and this principle of mediocrity, certainly they kind of push physicists, I think, and it's my experience, that we're kind of optimistic on this topic. And we allow our imaginations to kind of run riot in terms of not only there being life, but also intelligent life. And it's obviously a part of human culture, and an important part, to think what that life might be like. How might they be similar to us or different from us? What would we learn from contacting these civilizations? If you talk to a biologist, for example, you probably get a different perspective on this topic. And, I'm definitely outside of my area of expertise, but at the moment we don't really have a theory of life. So we don't really know all the steps that were required to take place in order for life to emerge on this planet, sort of going from chemistry to biology. We know that, at least as we understand it, that it's a pretty complex, multi-step phenomena. That's the way biologists try and understand it. And that potentially some very rare things have had to happen in order for life to emerge. And we know that it cannot be that common because, we don't see life sort of spontaneously arising around us. Unless it's already there, it just doesn't spontaneously arise. So biologists will argue that could actually be a very random event for life to emerge, and that intelligent life is even rarer than that. And beyond that, a technological civilization is again another step, which is fairly based on fairly sort of previous random steps, and so might not be repeated, even though we have these huge numbers. So I think some biologists will argue that huge number of planets, if you take the inverse of that, then that's a probability that intelligent life would emerge somewhere, given the conditions are right. Which kind of implies that we could be, potentially the only sort of technological civilization, at least in our own galaxy. That's not beyond the realms of possibility, at least from a biologist perspective. Now I think you can counter that by saying, well, we don't actually understand, we don't have a theory for life. We cannot create life in the laboratory, for example, although we might be getting close to being able to do that. And one other thing that we do know is that at least on this planet, life arose just as soon as it possibly could, which is kind of encouraging. It might just be that's the way it was. It might not be repeated anywhere else, but at least on this planet, we know that simple life emerged very quickly. But we also know that intelligent life took a long, long time to develop. So we've only really had complicated life on the planet for the last sort of 500 million years, at least on the surface of the planet. And we've only had technology for the last, say, 100, 200 years. So anyway, that's kind of a little bit of background. Another thing that you can try and be a bit more positive about is that even if sort of abiogenesis is actually a kind of rare event, it doesn't have to happen everywhere. We know that we are exchanging material between planets in the solar system, for example. So if we detect life on Mars, there's no way of knowing whether it originated there or it originated here on our own planet. And even now there's speculation, because we've detected the first interstellar visitors like Oumuamua a few years ago, that stars are also exchanging material. Fred Hoyle, brilliant astrophysicist, had those ideas a long, long time ago, almost 100 years ago, that potentially life could be being exchanged between the stars. So I'm not too negative about it, but I do realize that a technological civilization might be something that's quite difficult to detect. And so you have to be beware of that when you start thinking about how you might go about detecting that kind of phenomenon. Oh, and then, yeah, just a nice little video of Oumuamua doing a tour of the inner solar system. And I think Arthur C. Clarke, and I'll mention Arthur C. Clarke a couple of times in this talk. You probably know he wrote many books. He was very much interested in spaceflight, very much interested in sort of thinking about the future and how technology developed. But I like this quote. He says, two possibilities exist. Either we are alone in the universe or we are not. And both are equally terrifying. And I really agree with that. If we are absolutely alone in the universe, then that seems to me to be a really kind of scary thing, that we are the only intelligence in the universe. It seems a lot of responsibility to put on the shoulders of one species, especially this one, if you see the way things are going at the moment. And equally terrifying is the idea that the universe might have lots of intelligent life out there. So we wonder, what will they look like? Will they be friendly? How will they think? It kind of blows your mind just working out what their culture would be, what their music would be. Do they have the concepts of love and religion and all the kind of stuff that we have? Is hugely interesting, but also at some level terrifying if they're very different from how we are, even if they just look differently, very different from us. So just to sort of go back a little bit to the history of this topic and the search for extraterrestrial intelligence, it kind of really began, at least in modern times, in the 1950s. So these two scientists, Philip Morrison and Cocconi, they realized sort of in the late 1950s, because they were aware that in the bottom right of the slide you see Sir Bernard Lovell and the Lovell telescope, as it's now known, behind him. They realized that if you had two of these telescopes, one on one planet going around a star and another telescope on another stellar system on another planet, that you could actually, if one was receiving and one was transmitting, that you could actually send signals that would be detectable across sort of really sort of large distances. In fact, distances that are on the interstellar scale, so hundreds of light years, thousands of light years even. And so they published this very nice paper. If you haven't seen it before, it's well worth having a look at if you're interested in the topic. And they pick up, apart from the general concept, they pick up a few things that have become things that have actually sort of happened. You know, first of all, they suggested that, you know, an area in the spectrum to look at in particular, because obviously we don't know, you know, where any civilization would be transmitting, the frequency in which they would transmit. But they kind of recognized that even then, that neutral hydrogen and the emission, radio emission it produces at 1420 megahertz was very important, sort of astrophysically, and it's probably even more important now than it was back then. That would be a kind of obvious area in which you could center your observations, at least to begin with. And they did the calculations that show that, you know, you can have a chance to detect the signals, but they also recognize that probably you begin by looking at the nearest stars, the ones that are closest, so that you had the best sensitivity for a detection. And last but not least, they have this very nice quote at the end of the paper, which people still bring out, especially if you're feeling a bit pessimistic. And you know, the fact that SETI searches, such as they are, have not had any success so far. Then this quote that, you know, the probability of success is difficult to estimate, but if we never search, the chances of success are zero. And I think that's still kind of the mantra of a lot of people that are in this sort of topic, is that, okay, we've been doing this for quite a long while. I think we've been doing it actually spectacularly badly, to be honest, until recently, till the last few years. But that it's such an important question that you know, we can't really stop, we can't afford to stop the search, and we should continue. And well, if you just go through the numbers, if you have these two telescopes, say, you know, one going around one planet, the other going around another planet in two different stellar systems, and you have a transmitter with a power PT, and you're separated by a distance d, and the telescopes have the same collecting area a. Then there's this equation which is sometimes called the radar equation, but more formally known as the Friis transmission formula, that you can work out what the power received will be if you know what the transmitting power is, and what the distances are, and what the area is of the telescope that's sending the signal. And if you put those numbers in, so say you assume a 10 megawatt transmitter, which is probably roughly equal to the most powerful transmitters that we use for radar systems, for example. Then if you locate that transmitter on the nearest star on a telescope like the Lovell telescope, then you can detect that signal with a signal to noise ratio of about 1,000 in 1 second. So of course this is the nearest star, but it gives you an idea of, you know, it's pretty easy, certainly with nearby stars and even quite distant stars, to actually be able to detect these kind of signals. Now I want to kind of broaden that out a little bit to think about, you know, energy intensive civilizations, what they do. We only have one example, which is our own at the moment, but it's quite instructive, especially the way things have evolved over the last 60 or 70 years. So at the moment, we're kind of swathed in a background of radio waves. So I'm pretty sure that all of you that are listening to the talk today are in a room that's completely filled with radio waves, you know, from you know, the different devices that you're using, the laptop or the computer that you have in front of you, your cell phone, your Wi-Fi, microwaves. You know, basically, radio is the premier way that we communicate on the planet at the moment, and it's been like that for 100 years. And there's probably good reason to believe that it'll continue like that at some level for another 100 years, just because of the properties of long wavelength electromagnetic radiation. And not only is it confined, it's not confined just to our own planet, but we're kind of moving outwards. So we have these huge constellations of satellites and even mega constellations of satellites that are now being planned, and they're all transmitting at radio wavelengths, typically at centimeter wavelengths. And sort of slowly but surely that'll creep up from gigahertz frequencies into the terahertz frequencies, at least in space. So we have this kind of low-level background coming from many, many, many relatively low-power devices. So the mobile towers are probably the most powerful. They're about 100 watts of power isotropically being emitted from them, down to your cell phone, which is probably less than 1 watt when it's not transmitting, at least. So, but you've got billions of these things. So compared to 30 years ago, this sort of background radio level is huge. It's enormous compared to what it was, say, in sort of 1960 when Cocconi and Morrison were thinking about SETI. So things have changed a lot. We have this broadband, very low level radio wave from many, many devices. In fact, the many, many devices actually makes the background actually quite considerable. But in addition to that, we still have actually very powerful sort of rarer events in the radio. And just a couple of examples here. The first one is the fact that we need to transmit signals to spacecraft that have very small antennas and are very, very far away. So the Voyager spacecraft, for example, are good examples of the New Horizons spacecraft, another example. So you need radio telescopes that have very high gain and very powerful transmitters, and you point them at the spacecraft. So we have a lot of sort of high gain, very directed radio transmissions on top of this very broad sort of low level emission. And we also have civilian and military radar systems, which are also not quite broadband, but certainly extremely powerful. So over the horizon radars looking for ballistic missiles, for example, extremely powerful systems. So that's kind of the radiation that we're producing at the moment in the radio domain. Sort of, on one hand, a sort of background created by many, many devices, and on the other hand, some rare, very bright sort of events being produced by radar systems, for example. And in a sense, this is not just confined to the radio. This is happening across the electromagnetic spectrum. When you have a civilization that uses a lot of energy, then typically the kind of things that they are doing means that that energy comes out in different parts of the electromagnetic spectrum, depending on what you're doing. For communication at the moment, it's sort of typically at longer wavelengths, because longer waves are very good at going through walls or through windows or round corners, or even through wooden doors, etc. But we're also sort of producing other signatures of the fact that we have a technical civilization. And apart from the radio, we also are producing a lot of infrared, a lot of excess infrared emission. And we're doing that because, oh, sorry, hold on a minute. Someone's calling me. Sorry about that. Oh, hold on. Hi, Meta. I'm giving a talk just now, but your mum's not home. But maybe. So I'll do that after the talk. So yeah, so we're not just producing radio wave, we're producing waste heat radiation, and so that might be something that other technical civilizations also do, because it's really, really difficult to not produce this kind of no matter how efficient your technology is, it becomes, if you want to reduce the amount of waste heat that you produce, it actually costs a lot of energy to do that. So why would any civilization sort of do it? And we're all familiar with this, you know, when we use our laptops or our computers or mobile phones, that when we use them, one of the byproducts of all those electrons flowing through a sort of nice, sort of concentrated form of energy that we have in electricity, once we do work with that to do computations, then it sort of emerges as heat energy. And that's just sort of fundamental laws of thermodynamics that are difficult to escape from without spending a lot of energy to do it. So at the moment, in conventional SETI or technosignature research, we're looking at these sort of three main areas: the radio, the infrared, but also the optical, which is on the right-hand part of the presentation. And in particular, looking for laser emission is very interesting. It's a way that we might communicate in the future, especially if you get above the atmosphere. It might be a good way over relatively sort of sub-interstellar distances to communicate. So those are kind of the three main areas: the radio, the infrared, and the optical, where we're looking for these sort of detectable techno signatures of advanced civilizations. And I think one thing certainly to take from this presentation is that this is really a very interesting area of research now. And it's interesting really for several reasons, but I think the major reason is that the gentleman that you see just off from the center of the screen next to Stephen Hawking, that he has invested $100 million into SETIs, called Yuri Milner. He's a Russian American. He made a lot of money in Silicon Valley, and he's invested some of that in thinking about how we search for life across those three main domains, especially the radio and the optical. And these are some of the instruments that have been used for that. And the project is called Breakthrough Listen. And I think it really transforms the way that we've been doing SETI. We're now doing SETI in a really systematic way, the way it should have been done, I think, before, but really never was. And so because of that systematic approach, and especially the approach of not just making the observations, but actually looking at the data, that we're much more likely to detect a signal now than ever before. It's hard to sort of evaluate just how much more likely, but it's probably many orders of magnitude compared to how SETI was done in the past. And partly as a result of that, you find that there are many astronomers getting interested in the field. They might not be doing sort of radio SETI or laser SETI, but just interested in some of the research that's associated with that. So there are a lot of good papers coming out, and a lot of them appearing in sort of your normal standard astronomical journals, which is really good. It's just a complete rejuvenation of the whole field, and that's going to increase. You know, we really are in this sort of era, at least an anticipated era, where we have all these wonderful instruments coming online. And as I mentioned before, the instruments will be producing huge amounts of data, sort of on unparalleled scales. And so we're going to find things that we don't understand. And some of those things might actually be related to advanced civilizations, because these instruments are really so much better than anything that have gone before, that we are probably on the verge, certainly within our own galaxy, of being able to pick up those telltale signatures just in normal astronomical data. So we have to, even if you're not interested in the topic, you have to be aware that potentially astronomical data could end up corrupted in this way. So let me just say something about the research we've been doing in Manchester. These are just some papers that have come out over the last year. I'll focus on the ones that I've been involved in and myself, but it's clear that you see this even in Manchester, that there are a few people doing stuff that wasn't kind of happening a few years ago. So this is the first one. So this is some work I did with Bart Wlodarczyk-Sroka. He was a master's student at the University of Manchester, and over the last year we were thinking about, you know, how SETI actually sort of does its stuff, and what kind of assumptions does it make. And there's one assumption that has always annoyed me, and that is that there's a kind of simplification that when you do SETI, when you look with a radio telescope for artificial signals, you kind of assume that you're looking at one single star in the field of view. But in fact, that's not true. So if you go out tonight and you use the Lovell telescope and you point it up at the sky, then it'll be sensitive to an area about the size of the full moon. So anything there that's producing radio waves, it can detect. Not just the thing that's in the center of the field, but things that are around the center of the field out to about half a degree or so. So we basically reanalyzed the most recent Breakthrough Listen data, because we realized that not only were there all these stars that we were also sensitive to, but we knew that because of the new instrument, Gaia, which is measuring distances to stars very precisely using geometric parallax, that not only were those stars there, but we knew the distances to all those stars. So there are something like 2 billion stars for which Gaia has measured their distances. So we could use this to actually put much more sort of tighter constraints on the prevalence of very powerful high duty cycle transmitters. So these transmitters need to be on almost all the time. The prevalence of these within 200 parsecs. And you can see that the prevalence is low. Although you're asking a lot, you're asking for very powerful transmitters, and you're asking them to be on all the time, basically, so you can detect them. It doesn't matter where you're pointing. But it suggests that you probably have to look at quite a lot of stars in order to make a detection. And that's one of the things that Breakthrough Listen is doing. So it started off with something like 1,500 stars. We, with this paper, brought it up to something like 100,000 stars. And the next step will be going to 1 million stars, and especially nearby stars. And that's the next step for Breakthrough Listen, using the Meerkat telescope in South Africa, which hopefully we in Manchester might also be very much involved in. So, and this is just a nice artist's sort of graphic to go along with that, just showing the idea that we're not just observing one star with a SETI radio observation, but we're actually observing many stars. And in fact, we're actually observing galaxies as well. We're observing everything that happens to be in the field of view. And if we can take account of that, we can say some quite interesting things. Now, going back to the waste heat generation and being sensitive to that, I was also working with a student, Hong Ying Chen, and we were basically looking for galaxies that have an excess of infrared emission. So they're brighter than you would expect in the infrared. So you know a lot about these galaxies. You know that a normal galaxy has a certain sort of spectral energy distribution, and in particular the ratio of the infrared emission to the radio emission in the galaxy. That tends to be the same number for the same type of galaxy. So for normal galaxies like our own Milky Way, the emission that you measure, say at 22 microns, which is what we're plotted here, is a few times brighter than the radio emission. And that's what you see for galaxies. And that's because the radio and the infrared are both being produced by the same process, which is star formation. or massive star formation. They're both related to massive star formation, either the birth of stars or the deaths of stars. So that's why the number is roughly the same. So you have normal galaxies sort of in this band, if you look at the ratio of these two quantities. And then you have these other galaxies. These are what are known as radio loud galaxies. So these are galaxies, they're not sort of, most of the energy is not being produced by star formation, but it's actually being produced by accretion onto a supermassive black hole. And one of the things that you get often from that is you get very large jets, relativistic jets of radio emission. So they produce much more radio emission than a normal galaxy would sit. And so they sit in this lower part of the diagram. And then there's something else. If you have galaxies which are sitting up at the top of this plot, then I think, at least with my argument, is that they can only be Kardashev type 3 civilizations. So they're producing, at the bottom we have things that are producing lots of radio waves. At the top we're producing something that's producing a lot of infrared. And that might be a telltale sign of Kardashev type 3 civilizations. And if you don't know what a Kardashev type 3 civilization is, I don't really have time to go into it, but you have a type 1 civilization, which is something like ourselves in terms of our energy use. You have a type 2 civilization that would be able to harness energy on the scale of a star, so about 10 to the 26 watts. And then you have type 3 civilizations that can harness energy on the scale of the total energy of a galaxy. So we don't find any evidence for Kardashev type 3 civilizations, which you might not be surprised about. Maybe you think it's a bit far-fetched for civilizations, to exist or even to require that kind of energy demand. But there's nothing to stop it. There's no physics that would stop Kardashev type 3 civilizations actually arising. But we don't see much evidence for them. So that's the stuff that we've been working on. Most recently, we just submitted a paper on that. So I want to talk about SETI and astronomy. I have this personal feeling that sometimes astronomers can be over-focused. We think we're talking about the big picture a lot of the time, trying to understand the universe, but we're often only looking up the way. And we don't often look at what's actually happening sort of down here on this planet. So on this slide, you see, your typical sort of, there's the Hubble Space Telescope observing the universe, trying to make sense of it, big picture. But we sometimes are guilty of not understanding that actually what's happening on this planet is very important. This planet, and it's the form of this planet, has been completely modified by the fact that there's life on it. It wouldn't and didn't look like this until life arose. It's only in the last billion years it completely transformed the atmosphere, for example. We've only had oxygen in the atmosphere for the last billion years. For the first 3.5 billion years, there was no oxygen in the atmosphere. And we've completely changed also not just the sea, the oceans, but also the land, due to the fact that we've had life on it. So life is important actually for understanding the big picture, and I think the big picture also includes whether elsewhere in the universe there are other intelligent beings also thinking about astronomy and all the other topics that we as human beings are very creative in. And I think Stephen Hawking kind of put this, I think he put it quite well in this quotation, which is, to understand the universe, you must know about atoms, about the forces that bind them, the contours of space and time, the birth and death of stars, the dance of galaxies, the secret of black holes. But that's not enough. These ideas cannot explain everything. They can explain the light of the stars, but not the lights that shine from planet Earth. To understand these lights, you must know about life, about minds. And I think that's why and I'm not on a crusade or anything like that, but I do feel that sometimes astronomers are very dismissive of SETI and thinking about life beyond our own planet. And I believe that if they were more open to it, they'd actually see a bigger picture. And actually there is this tension, I think, in the community where, so you have people like Shklovsky, of course, a great Russian astrophysicist, and I think he sort of espouses the traditional view on this topic. So he said any phenomena should not be declared artificial before all the natural explanations have been completely exhausted. And I think by and large, the astronomical community kind of abides by that principle. And if people shift from that principle, and there's been a few examples of that recently, for example, Avi Loeb, famous cosmologist, who also has dabbled in many other different areas, including suggesting that Oumuamua might be one of these sails, interstellar sail, rather than interstellar comet, then they typically get shot down, which which I don't actually like and I don't agree with. And here's another famous Russian astrophysicist who was the student of Shklovsky, Nikolai Kardashev, who we've just mentioned before. He has a very different view on this. He's a very special guy. And he says the presumption of naturality of every astronomical object is coercion over creativity. Each scientist has the right to work within the framework of their belief system and intuition. So it's interesting. I just want to bring it up because I think there's an interesting tension about this, and it especially comes up when you're searching for extraterrestrial civilizations. And well, I guess this cartoon, I hope, kind of sums up a little bit some of the things that I've been talking about. If not, I hope it's just funny, but yeah. So anomalies in astronomical data. You've probably heard of Clarke's third law. I guess this is the third time his name has appeared on a slide here, at least. And his third law is that any sufficiently advanced technology is indistinguishable from magic. You know, if we were to go back in time and take, you know, our mobile phone even 100 years ago or 200 years ago, people would not really know what it was. We would appear to be sort of, you know, being able to be capable of doing magic, calling people across the world, seeing people's faces, etc. So we shouldn't think that a civilization that might be thousands of years more advanced than we are couldn't put up the same kind of show for us. And this brings me on to this sort of general topic of looking for anomalies in astronomical data. And one of the most sort of simple things that you can look for are, you know, impossible phenomena, things that really shouldn't be happening, that might appear to be magic to us, that defy any natural explanation. And there's an interesting paper, 2 papers on this now by Vila Roel, and she has written this paper on vanishing and appearing stars. She's written it partly just to look for very interesting extreme objects, but she's also written it because she's interested in the search for extraterrestrial intelligence, if the truth be known. And so she's looked at sort of old photographic plates from the US Naval Observatory from 1950 and has been looking for stars that have either disappeared or have appeared over the last 70 years. So she's looked at 600 million stars. She's found something estimated to be something like 700 interesting candidates. Exactly what these candidates are, we don't know. She's looked at some of these very carefully. But you know, they may just be microlensing events or M-dwarf stars that flare, although she feels as though there was no obvious evidence for this in data up until the point at which they disappeared. So she certainly leaves open the possibility that at least this kind of technique could be sensitive to stellar engineering, so construction of Dyson spheres around stars, which would cloak a star, if you like, would make the star invisible, or the creation of stars using laser communications. The star might appear there just because of very powerful laser in operation at that point in the sky. So that's sort of interesting start in this area. Another anomaly is probably Tabby's star. You probably all know about that. This star where the dips in the light curve due to something transiting across the star are enormous. So normally for a planet they're, you know, a few percent or less, but here the dips in the brightness are 15%, 20% even at some stages. So initially that was thought it could be some kind of megastructure passing in front of the star, but it appears, again, because the variability is chromatic, it depends on the wavelength that you observe at, that this is probably dust. Although exactly where the dust resides is still a sort of open question. And as I mentioned before, with all these survey instruments producing huge amounts of data, we're going to find lots of anomalies in astronomical data. And these are some of the things that we could be looking at. I won't go through them all because I don't really have enough time, but I just sort of list them: looking for megastructures passing in front of stars, looking for spacecraft with sort of incredible proper motions, looking for Dyson spheres because the spectroscopic distances and the geometric distances don't agree with each other. Sort of clusters of similarity in the sky. If you saw the same phenomena in a particular patch of sky, that might be a sign of some kind of galactic lighthouse. Unnatural patterns of variability, missing transits, for example, where you expect a transit and you don't see any. Stellar types that are excessively bright at some wavelengths, for example, have a broadband radio component that they shouldn't have. Most main sequence stars don't produce a lot of radio emission, for example. Unusual variability profiles, non-spherical bodies, so things which have odd shapes or sort of geometric shapes like a megastructure or whatever. So there's many of these things that could provide these sort of anomalies in astronomical data, and people are beginning to look for these, and particularly we'll look a lot from the telescopes that will come online over the next few years. And very much a kind of also within SETI, even the traditional side of SETI, the idea that we need to widen the net, that we need to think more openly about where we should be pointing our telescopes. That's also coming in. And I point you just to this paper, which is essentially looking for life where you would not expect to find it, rather than looking for life where you would expect to find it. I think it's really quite instructive. So one thing that I think is important, and I like this quote from this report, which says, you know, nothing would be more tragic than to encounter alien life and fail to recognize it. We sometimes overestimate our senses, our cognitive power, to be able to do this kind of thing. You know, we think we're almost invincible. We think we can work out, you know, the cosmology of the universe, etc. Even though we share 99% of the DNA of a chimpanzee, we think that, you know, something sets us apart to be able to understand just about everything that there is. But that might not be true. And maybe this is one of those topics, sort of actually being able to identify life, especially intelligent life forms, might be something that we're not very good at, although it might be there. Again, another cartoon suggesting we might just be a little bit over-focused on things. So I apologize for the diversity in this cartoon. We do have a few more women in astronomy than is pictured here. And actually that diversity is really important, because it's that diversity that actually allows us to begin to think more broadly. Maybe this cartoon actually sums up the fact that diversity is more and more important, especially in this field. And you can take that diversity to a different domain where we don't talk about biology, but we also talk about our machines. We know that we have the rise of machine intelligence, AI and machine learning, etc. We know that to do astronomy, we have to use these tools in order to identify anomalies. We know that machines probably have less bias than we have. If they can begin to think for themselves at some level, then they may actually be much better than we are at being able to look for anomalies and even be able to identify intelligent life out there. So that's something to look forward to, that it might be our machines searching for their machines rather than us calling all the shots. And I also want to mention that you know, that astronomers in particular are always looking in the past. We're always going backwards in time. We don't often go sort of towards the future, but there is a fantastic future out there. We're here in this slide today, but even within the solar system, you know, there are a couple of billions of years of interesting things, 8 billion years of very interesting things that will happen. It can't be that things just remain the same as they are in this particular instant of time. They could become even more interesting. There might be something else out there that's even more interesting than what we understand to be normal at the moment. You probably heard this quote from Carl Sagan from the Cosmos series, you know, very, very Carl Saganish, you know, we are a way for the universe to know itself. And that could be true. It seems a bit kind of highfalutin for me that we would be the only way for the universe to know itself, that there could actually be many other ways to try and understand the universe, or other forms that are trying to understand the universe, all based on those cosmic foundations that come from the creation of the universe. And I'll admit to being very speculative here, but perhaps there are other kind of forms of intelligence, other kind of branches, flowers of intelligence that are quite different from ours. We should be open to those kind of ideas. We already know that, you know, even in our own little worlds, we understand that there's the biological intelligence, that there's this new thing which could form its own intelligence, you know, machine intelligence, and could become independent of us at some point in the future. Probably will be, if we think about it sort of carefully enough. So we've already kind of encountered probably two forms of intelligence, one of which, if I'd mentioned it maybe, you know, 30 years ago, people wouldn't really have believed was possible. But actually, it's even doing our astronomy for us at some level at the moment, and that trend will continue. But you can be even more speculative and think that there's actually some other branch of intelligence that manifests itself in the universe to try and understand the universe, for the universe to understand itself. And either we don't know how to identify it, you know, or it's not in our locality, but it might still be out there. So in kind of wrapping up, one thing I like about this topic is that SETI challenges are fundamental ideas, I think, about the universe. You know, this idea that there's nothing, you know, the Copernican principle, it challenges the Copernican principle. You know, is there really nothing special about us and our planet? Well, maybe this is the only place in the whole cosmos where there is intelligent life. Maybe this is the only place where people, you know, have produced music and written books, that, you know, have loved each other, have done all the special things that we do, have tried to understand the universe and how it arose. It's quite possible that this really is a very special place, and that means we need to think about the future, I think, if it is the case, even if it's not the case. You know, we know that there are a huge number of challenges facing humans, certainly over the coming years, and you'll be familiar with many of these, I think. The fact that we're using resources unsustainably, that has to stop at some point, you know, otherwise society will collapse if it hasn't become sustainable, and that'll probably happen in you know, this century if we don't really do something about it. I was at a workshop about a month ago. I was struck by, you know, this statement by a biologist there that 75% of species will be extinct within the next 250 years on our planet. So that's basically the definition of mass extinction when you get to 75%. So we've already, just through our own ability to modify the environment, we've already started a mass extinction on the planet. So we kind of seem to be at this point on this knife edge. And you know, most of you listening, I think, are the generation that can actually make a difference to all of this. You will be the sort of leaders and scientists of the future. You know, on one side, it could be self-inflicted extinction, or on the other side, it could be sort of interplanetary control. We might be able to control our environment so that we can, you know, essentially live forever, at least as a species, that we can settle parts of the solar system, for example, so that we have independent instances of the species that can go forward. That's certainly a positive view of things, although it's hard to see it happening at the moment, but there are some interesting things. And again, this is my second last slide. We do need to take better care of our planet, as I mentioned before, but we also need to take better care of each other. And that's very easy when we're taking care of our friends and our families. But it's more difficult when it's actually everyone else, so everyone else on the planet that also deserves a share of the resources of this planet. We need to get away from the idea of borders and of differences. We need to celebrate the things that we have in common and think about how we can go forward in the future to make sure that potentially, you know, this harbour for intelligent life has a way forwards, a trajectory towards understanding the universe beyond where we are at the moment. But that means that we need to make some difficult choices in the coming years. So I'll leave it there. Thanks again for asking me to give the talk. And I just want to finally mention that we have a course given by USL, Are We Alone, which is open to all undergraduates. Maybe some of you have taken it. If not, then please take a look at it, and you'll come across some of the topics that I've talked about today. You'll come across in much more detail in this unit. Thank you.
Thank you so much. It was really interesting. I think people might have some questions. They can put them in the chat, or they can raise their hand and unmute themselves.
I'll just unshare my screen so that I can see the... No questions, right?
I do have a question if
Okay.
no one wants to go. Yeah, so many times when talking about SETI, people mention that we may not want to be detected by other civilizations, so that they might not be friendly. But
Yep.
would that pose an actual threat? So if a civilization was technologically advanced enough to be a threat to us even light years away, wouldn't they have detected us already?
Yeah, I mean, it's I think certainly if they were nearby, they almost certainly have detected us already. Stephen Hawking had kind of strong views on this. I think that he felt that people shouldn't be trying to broadcast the fact that we are here. And there's a group of people that conduct what's called METI, which is messaging sort of extraterrestrial intelligence. So SETI is passive, we're just looking for things, so receiving radio emission, but there's also a sort of smaller group that are interested in METI, sending signals out there. And Stephen Hawking was definitely felt that wasn't a good idea, and that he worried that, you know, there will be civilizations out there that will take this as an invitation to come and eat us up, kind of thing, you know. Personally, I don't personally have much time for METI, in the sense I feel that a lot of the people that are doing it are just doing it for publicity. And it's not really very scientific. You know, I don't hear of any people sending messages to a star 8 light years away, and then coming back and trying to listen to see if there was a response. There's an awful lot of just publicity associated with sending messages, I feel, so not very scientific. But yeah, it has to be said, as I mentioned before, we are modifying our environment, and we are sending out extremely powerful radio transmissions. I would normally reference Arecibo, but since Arecibo isn't here any longer, but there are other radio telescopes that do, for example, planetary radar. So Goldstone and the DSN is one that would typically often have a very powerful transmitter, and it would illuminate solar system bodies, and then Arecibo would map them, would map the reflection. So for scientific purposes, also the ionospheric research that Arecibo did, when it heats up the atmosphere at low radio frequencies, well, those radio waves also go into space, and they are really, really bright when they go into space. And then there's just all the DSN traffic to spacecraft out there that are quite distant. So, and yeah, in my view, a little bit of METI doesn't really make any difference to all the stuff that we're doing already. And I don't honestly think, personally, that intelligent life is prevalent enough that it's on our own doorstep. I'll probably be proved wrong tomorrow morning. There'll be something will be discovered in the solar system. But I think that probably, if there is intelligent life out there, it's probably relatively far away from us. And so I think the chances of something horrible happening are probably not that high, but you never know. Yeah. Yep.
What do you think the odds on Arecibo 2 are? Do you think they're going to be able to rebuild? I took this earlier this year and was rather pleased with it. So
it's not bad. Yeah, it's nice. Arecibo 2. So I haven't really been following it very closely, partly because I have my own. I honestly have my own opinion on it. I think Arecibo was a fantastic instrument when it was built in the 1960s, and it served the community extremely well for a long, long time. Especially the pulsar community, I think. Transient community less so, but certainly the pulsar community. I doubt if you asked a pulsar astronomer, I don't know how much Arecibo would cost, but I'm guessing you're talking about something that must be about $200 million, or
that's about it. Yes,
right.
That's what I've heard.
Right. It must be something of that order. I think if you ask the pulsar astronomer what they wanted, they wouldn't want another Arecibo. They'd want something more like the SKA, so small dishes and many of them. Partly also because the Chinese have the fast system, which will be, certainly when it's operational, much more capable than Arecibo. So you certainly wouldn't want to build. You'd want to build some. If you're going to build a single dish, it would probably be something like like fast, rather than Arecibo. But I think the cost is so large that it might help fund the NGVLA, the next generation VLA. The fact that there's no Arecibo, it might just make that sail through the upcoming decadal report, and maybe that's the kind of present that the US astronomical community will get, rather than another Arecibo. And also that site of Arecibo is actually a very poor site for radio frequency interference. They have a lot of radar on the island, and there's a lot of military activity in that area as well, and surveillance. So you probably wouldn't build it there, and that would be what people from Puerto Rico would be most interested in, is building it there rather than building it somewhere in the southern hemisphere in the desert somewhere or other, which would be or maybe in Argentina or whatever. And that would be the appropriate place to build an Arecibo 2. So I honestly don't think that it will happen.
Thank you.
We seem to have 2 questions in the chat.
Yeah.
So G10 is asking, from a more pessimistic point of view, is it possible to ever confirm an anonymous observation as extraterrestrial life when there's a lot of different astronomical processes that are complex and less understood?
Yeah, I think that's a good point. We definitely don't know everything about astronomy, so we might find something that's anomalous that we might not understand that astrophysically, but it could still be astrophysical. There's definitely a danger of that, and you see that in the discussions that have been taking place about not technosignatures but biosignatures. So the idea that if you detect oxygen in the atmosphere of a planet, which is a really difficult thing to do, but you might be able to do it for the nearest stars with the extremely large telescope, the European extremely large telescope, the EELT. You might be able to do it if you sit on it for a long time. That even if you did detect oxygen, would you really know enough about planetary systems that you couldn't think of a way of having oxygen in the atmosphere, maybe for a brief amount of time due to some kind of geology or geochemical processes that we don't understand or that don't occur on this planet but might occur on other planets? So I think you do have to be careful. I think if you made the observations and you found that planet had supporting data, that it had a temperature roughly around the freezing point or above of water, that you also found other biomarkers in the atmosphere, etc. If you had supporting information, then perhaps you can make a good claim that oxygen is being produced by biological processes. But if it was just oxygen on its own and you didn't know much else, I think it's quite difficult, and that'll probably be true of just these generic anomalies that I was talking about earlier, that they could indeed be misinterpreted. So we'll definitely have to be careful, but there's going to be so many anomalies out there that it's going to be very interesting.
We have another question by Kelvin. What do you think about the great filter hypothesis?
Yeah, so I think it's so just to explain, that there's this idea that you have life and it evolves, and during the course of that evolution there are some places where there are kind of difficult things need to happen before you get to the next stage. So an example on simple life might be, how do you form sort of a cellular structure or a multicellular structure? How do you make that step? Does that step not happen not very often? And going beyond that, when you have an intelligent civilization and maybe a technological civilization, another filter might be, well, how long does a technical civilization sort of live for before it does something terrible to itself, that the civilization collapses, right? And maybe there are other sort of these filters that, in the end, there are so many of these filters that at each stage, the number of sort of intelligent life forms or life forms of any kind becomes smaller and smaller, smaller and smaller and smaller, until you've just got a few, or maybe even just one civilization that passes that last filter. Maybe we're in that situation where we have passed, I doubt we've passed the last filter. We've probably passed many filters. For example, in the 1960s, we certainly had the ability to sort of destruct, you know, with nuclear weapons, probably the first time we could actually do that. We haven't done that so far. It doesn't mean to say we might not do it in the future. And what we've seen over the last few years is there are many other potential catastrophes that could be that filter. It doesn't have to be sort of a nuclear accident or whatever. We know that there's going to be a battle for resources if we continue to use them unsustainably. You see it with water between China and other Asian nations there, that's already started. So yeah, the filter might be in front of us. It might be behind us if you're really optimistic, but I suspect there's certainly a few filters in front of us before we become kind of truly spacefaring, even in the scale of the solar system. So it's definitely an interesting way to teach things as well. I think we use it in the course that I do as well. So I think it's an interesting hypothesis and a useful way to think about things sometimes.
Is there any other question? Otherwise, I guess if people have come up with questions, they could email you at some point.
No, absolutely. Very happy. We're always looking for students that are interested in doing this work for their PhD or their masters or whatever. So you can, if you Google me, or you'll find me, find my email address pretty easily, and I'm definitely happy to talk to people. We've had some interesting results recently, and I hope in Manchester we can have more results like that, and we want to involve students in that research as well.
We have one more question by Alice. Do you recommend any cool books on this? I'm actually a grad and can to do the course.
There are lots of books. I mean, there's so many books out there on the topic that I hardly read any of the books. I'll be honest with you. I think you would find a lot of interest on things like on the archive, AstroPH, or on NASA ADS. I don't know if, I guess undergraduates might be familiar with those kind of resources where you can access all the papers that are produced in astronomical journals. So yeah, if you just do a search on SETI or techno signatures in the abstract, you'll actually probably get stuff there that's pretty interesting and gives you a good background on all the things that have been thought about. One book that I found quite interesting recently was by Duncan, I think it's Duncan Frogan. What's it called? It's about the Fermi paradox. And although it's very kind of focused on the Fermi paradox, Duncan, he was an astronomer in St Andrews. Unfortunately, he actually left the field after being in the field for a long time. He left when he was had done several postdocs. But he's written a book on the Fermi paradox. So if you look on Amazon, you'll be able to find it. And one thing that I like about it is that it's kind of scientifically rigorous. So it doesn't need, but it has a little bit of maths and things like that in it to describe different sort of solutions to the Fermi paradox, and it covers in a sort of mathematical way a lot of the themes of SETI. And I actually think it would have been better written as a SETI textbook and forgetting about the Fermi paradox, but I suppose the Fermi paradox sells it to the general public. But have a look at that book. I'll type his name in the text just now. So it's Duncan Frogan. I think it's Frogan. And I think can't remember the title. I think Fermi paradox. Yeah, that's it. Forgan. Yeah, super. Great. So I would recommend that book. I don't know if it's in the library as a digital book. It could be. Could be.
Thank you very much. If there are no more questions, we can end it here.
Okay.
Thanks a lot for the talk.
Yeah, thanks. Been lovely. So have a good Christmas and hope to see you all soon.
Thank you.
Thanks.